Hi everyone. Today we're going to start chapter 19, which is all about electrochemistry. So in this chapter, we're going to discuss oxidation reduction reactions, and you might recall that we went over those types of reactions at the very beginning of general chemistry. Now, what we're going to do is expand on what we know and learn how we can use redox reactions to generate electricity. So there are a lot of different applications for these redox reactions. So we can use them in batteries and other devices. There's lots of different types of batteries that we can use. But we can also utilize them in fuel cells, for instance, and fuel cells might one day be our alternative source of energy for homes and cars. So currently, most homes and buildings, etc., they get their electricity from a power plant, for instance, and it's called a power grid, which distributes electricity throughout the country. So the average U.S. household currently consumes about 1,000 kilowatt hours of electricity per month. Now, of course, recently that's probably gone up since most of us are working from home, but that's a lot of energy, and some companies are trying to develop small fuel cell power plants, which are about the size of a refrigerator. And these fuel cells could power homes or businesses or cars. So fuel cells are actually based on a redox reaction, and down below that reaction is hydrogen gas combining with oxygen gas to produce water. So 2 moles of hydrogen gas will react with 1 mole of oxygen to produce 2 moles of water. Now, you might remember from a long time ago that we can show there's a transfer of electrons in this reaction by assigning oxidation numbers. So pure hydrogen gas would have an oxidation number of 0. Same for oxygen. But then once we have a compound of hydrogen and oxygen, hydrogen will have a value of +1 and oxygen will have a value of -2. Now remember that if something loses electrons, that's oxidation, and if something gains electrons, that's reduction. And we can use the acronym OIL rig to remember that. Or Leo the lion says grr, whichever one that you prefer. So if we look at hydrogen as a pure gas becoming then a compound, we're going from an oxidation number of 0 to +1. So are we losing electrons or gaining electrons? So we're losing electrons, right? We're becoming more positive in our oxidation number. So that means that hydrogen is experiencing oxidation. And then what about oxygen? Oxygen is going from 0 to -2 in oxidation number. So is that gaining electrons or losing electrons? It's gaining electrons, right? It's becoming more negative. So that will be our reduction there. All right, so this very simple reaction can be used in, again, fuel cells. And one is shown off to the right. And again, it's about the size of a refrigerator, so it's really not that big. If you have a water heater in your home, it's not much bigger than that. So in a hydrogen-oxygen fuel cell, the hydrogen and oxygen are separated. And that's going to force electrons to travel through an external wire. And then the electrons will generate a current. And these fuel cells will take advantage of the fact that oxygen gains electrons and hydrogen loses electrons. So that's going to force electrons to move through a wire, creating electricity. And this kind of electrochemistry, or these fuel cells, are actually being used in some cars now. So this is the Mirai, if I'm pronouncing that right, developed by Toyota. And actually in California, they're developing what's called a hydrogen highway, where if you have one of these fuel cell cars, you can just fuel up at one of those stations. But unfortunately, the hydrogen highway has kind of been stalled for the time being. However, the cost of these cars is going down as time goes on, so it could become more of a reality in the future. And then we won't have to depend on fossil fuels, for instance, which are currently decreasing in, abundance or supply. And that would be nice if we didn't have to depend on fossil fuels in the future. So let's talk a little bit more about these oxidation reduction reactions. So again, remember that reactions where electrons are transferred from one atom to another are redox reactions. And redox is short for oxidation reduction. So another example of a redox reaction is the reaction between sodium and chlorine, which will produce sodium chloride. What we can actually do is split up sodium and chlorine into their respective half reactions. So if we assign oxidation numbers, sodium has a value of 0, chlorine has a value of 0. Sodium, we're just going to assign it an oxidation number that's equivalent to its charge, so it's +1. And then the chloride ion would be -1. So sodium is going from 0 to +1, so it's losing electrons, which is oxidation. And then chlorine is gaining electrons, so that's reduction. And now that we know what's losing electrons and what's gaining electrons, we can write those half reactions. So for sodium, pure sodium is becoming sodium ions, and remember it's losing 1 electron, so we're going to write +1 electrons in the products. And then chlorine's half reaction, remember it's gaining electrons, so we're going to write that as a reactant, and then we're forming 2 chloride ions. So remember Cl2, that's a diatomic molecule, and chlorine is found as a diatomic molecule in its pure elemental state. Now, in order for chlorine to split apart into chloride ions, we need each chlorine atom to gain 1 electron. So that's a total of 2 electrons that chlorine is gaining, which is why we have 2 there. All right, so again, we generally split the redox reaction into 2 separate half reactions. So those are reactions involving just oxidation or just reduction. So remember, the oxidation half reaction has electrons as products because we're losing electrons, and the reduction half reaction has electrons as reactants because we're gaining electrons. So down below is another example of a reaction where reduction and oxidation are occurring. So we have 3 moles of chlorine reacting with an iodide ion and 3 water molecules to produce 6 chloride ions, an iodate ion, and 6 hydrogen ions. So if we go through and assign values to each of these, so oxidation numbers, chlorine is in its pure state, so that has a value of 0. Iodide has a value of -1, so that's just equivalent to its charge. hydrogen will be +1 when it's in a compound. Oxygen will be -2 when it's in a compound. And then in the products, the chloride ions will have a -1 oxidation number. And then we have a polyatomic ion, iodate. So oxygen will still have a value of -2, but there's 3 of them. So that will be an overall -6 coming from those 3 oxygens. Now, the iodine in iodate has to have a charge that balances all of the other charges. So we have I plus 3 times -2 for those oxygens, and everything has to add up to the overall charge of the polyatomic ion, which is -1. So I will end up equaling -1 plus 6, which is +5. And you can check my math there, just if you're not sure how that worked out. And then hydrogen as an ion, again, will just have a +1 charge. So hydrogen had the same oxidation number throughout, so that's not undergoing oxidation or reduction. Oxygen also had the same oxidation number throughout, so that also didn't undergo oxidation or reduction. However, chlorine went from 0 to -1, and that means it was gaining electrons, so that's reduction. And then iodide became iodate, so it gained electrons, or sorry, it gained oxygens, but it lost electrons overall, so that would be oxidation. All right, so again, we can take what we know about the transfer of electrons for a reaction and split up the reaction into oxidation and reduction, so the 2 half reactions. Now, you might also be wondering, where did these 6 electrons come from for the oxidation of iodide? Well, remember, iodide went from -1 to +5. So in order to go from -1 to +5, iodide must have lost a total of 6 electrons. So you could write that algebraically as well. So you could say, okay, -1 equals, let's see, iodide plus 5. And then iodide would equal -6. So we have 6 electrons that iodide lost. All right, so once we have half reactions for a redox reaction, we can also write an overall reaction, but first we have to balance the half reactions. So there is a method we can use to balance complex redox reactions in solution. So again, we break the reaction into 2 parts, or 2 half reactions, one for oxidation and another for reduction. And then each half reaction is balanced individually for both mass and charge. So we want to take into account how we would normally balance equations. Do we have the same number of atoms on each side? And are we following the law of conservation of mass? But then additionally, we want to also balance charge by adding electrons, either on the reactant side if we're gaining electrons, or on the product side if we're losing electrons. Then we're going to add the 2 half reactions back together. However, we do want to make sure that we're canceling out the same number of electrons from both half reactions. So let's look at some steps that we can take for these types of balancing problems. So in the first step, as we just saw, we would assign oxidation states. So we want to determine which element is oxidized and then which element is reduced. Then we write the oxidation and reduction half reactions, just like we saw before. And then when we're balancing the half reactions, let's say that we do have oxygen in either one of the reactants or one of the products. We're going to need to take that into account. So first we'll balance any elements other than hydrogen and oxygen. Then we're going to balance oxygen atoms by adding H2O where oxygen is needed. Then we're going to balance hydrogen from H2O by adding hydrogen ions where H is needed. And then if the reaction, If the reaction is in a basic solution, we have to neutralize the hydrogen ions with hydroxide ions. So this is something that's pretty complex, and we'll go over a few examples to demonstrate what this means, because right now I'm sure it's a little abstract. So then step 4, we're going to balance the charge of the half reactions by adding electrons. And then in step 5, we're going to make the number of electrons in both half reactions the same so that they'll cancel. So we might have to multiply one or both of the half reactions by some factor so that the electrons will equal each other. And then we're going to add the half reactions and cancel anything that's on both sides of the arrow. And then at the very end, we want to check our work by making sure atoms are balanced and also that the charges are balanced on each side of the arrow. All right. So we just went through a lot of rules. Let's actually use them in a couple of examples. So this example is in your textbook, but let's go over it together. So we're going to balance the redox reaction where aluminum reacts with copper ions to produce aluminum ions and copper. So this one's a little bit easier, so we'll start with kind of an easy one and then go into some harder problems. All right, so remember from the previous slide, we first want to assign oxidation states. So aluminum is in its pure solid form initially, so that would have an oxidation number of 0. Copper has a 2+ charge in the reactants, so that would be +2. Aluminum then has a +3 charge in the products, so that would be +3. And then finally, copper turns into pure elemental copper, so that would have an oxidation number of 0. Okay, so aluminum, if we just focus on that, its oxidation number changes from 0 to +3. So is it losing electrons or gaining electrons? It's losing electrons because it's becoming more positive. So this would be oxidation or reduction? Oxidation. Okay. And then what about copper? Oh, let's see, I'll do this. So copper, its oxidation number is +2, and then it becomes 0. So is copper gaining or losing electrons? Gaining. So is it oxidized or reduced? Reduced. Okay, so we can then write out the half reactions. So that's step 2, write oxidation and reduction half reactions. Let's see. Okay, so let's write the oxidation half reaction and the reduction half reaction. So oxidation, aluminum becomes aluminum 3+, and then reduction, copper 2+ becomes copper. All right, so now step 3, balance the mass of the half reactions. So really that's just saying to balance the atoms on both sides. So if we look at our half reactions, do we need to balance any of those atoms? No, we have one aluminum on each side for the oxidation reaction, and we have copper on each side, or one copper on each side for the reduction. So then the next step is to balance the charge of the half reactions by adding electrons. Okay, so let's do that on the next slide. All right, so oxidation, aluminum we know is going to lose electrons, so then we'll want to write the number of electrons that it's lost in the products to demonstrate that it's losing those electrons. All right, so how many electrons does aluminum lose? 3. So we're just balancing that positive charge on aluminum with 3 electrons. And now for the reduction reaction, where copper 2+ is going to gain electrons. So how many electrons does copper need to gain in order to become a neutral element? 2, because we want the positive and the negative charges to balance, right? So we want them to add up to 0. Okay, so now let's go back to our steps. So 5, make the number of electrons in both half reactions the same by multiplying one or both half reactions by a small whole number. Okay, so if we want these two reactions to have the same number of electrons, so let's see, in our oxidation reaction we have 3 electrons. In our reduction reaction we only have 2. So what can we do to make those even or the same? So we would want to multiply the first reaction by 2 and the second reaction by 3. All right, so let's rewrite those reactions down below and we'll multiply them by their respective factors. So for the oxidation reaction, now we have 2 aluminum going to 2 aluminum ions plus 6 electrons. And then for the reduction half reaction, now we have 3 copper ions plus 6 electrons, and then that's becoming 3 coppers. Okay, so now we can cancel electrons on both sides of the arrow. So if we go back to our steps, step 6, we want to add the half reactions and cancel like terms. So we're going to cancel the 6 electrons on the left side of the arrow and the 6 electrons on the right side of the arrow. All right, so now we can write our full overall redox reaction. So on the left side of the arrow, we have 2 aluminum, let's say atoms, and that's reacting with 3 copper 2+ ions. And I'm going to put the states back in here. And then on the right side of the arrow, we have 2 aluminum ions plus 3 copper atoms. So that is our balanced reaction. Now let's make sure that we have the same number of atoms on each side. So it looks like we have 2 aluminum atoms on each side and 3 copper atoms on each side. So that works out. And let's make sure the charge is the same on both sides. So I'm actually going to rewrite this equation. Okay, so we said we have 2 aluminum atoms plus 3 copper 2+ ions plus, and that's becoming 2 aluminum ions plus 3 copper atoms. So let's figure out the charge on both sides. So on the left-hand side, aluminum doesn't have a charge, it's just neutral. But copper has a charge of 2 plus, and there are 3 of them. So that's a total of plus 6. And then on the right-hand side, aluminum has a 3 plus charge, and there's 2 of those ions. And copper is neutral, so that would again be a total of plus 6. So everything is balanced in terms of atoms and charge. Okay, so now that we kind of have a feel for the different steps in this reaction, or in this balancing scheme, let's do something that's a little more challenging. So this is another example that's in your textbook, and in this example, we're asked to balance the redox reaction where iron 2 plus reacts with permanganate, MnO4 minus, and then the products are iron 3 plus and manganese 2 plus. All right, so I'm going to rewrite this so we can assign oxidation numbers. Okay, so iron in the reactants has a 2 plus charge, so its oxidation number is plus 2. So let's write ON there for oxidation number. Now in permanganate, which is MnO4 minus, oxygen is within a polyatomic ion, or another way to say that is it's in a compound essentially. So it will have a -2 oxidation number. Now there are 4 of those oxygens, so we have a total of -8 coming from those 4 oxygens. So now we need to determine the oxidation number for manganese. So I'm going to write a little equation. So manganese minus 8 has to equal a total of -1 because that's the overall charge on that polyatomic ion. So if we rearrange that, manganese is equal to -1 plus 8, and that's equal to plus 7. So manganese will have an oxidation number of plus 7. Okay, and then I'm just going to erase these extra little bits of math I did down here. All right, so then in the products, iron has a 3 plus charge, so its oxidation number is plus 3, and manganese has a charge of 2 plus, so its oxidation number is plus 2. All right, so now let's figure out what's being oxidized and what is being reduced. So we'll start with iron. So iron's oxidation number is plus 2 initially, and then it changes to plus 3. So has it lost electrons or gained electrons? So it's becoming more positive, which means that it has lost electrons. So it's, is it oxidized or reduced? Oxidized. All right. And then let's look at the other 2 elements here. We have manganese and oxygen. Now oxygen doesn't appear in the products, so we're going to ignore it for now. We'll come back to that later. So let's look at manganese, since we do have manganese in both the reactants and the products. So manganese initially starts out with an oxidation number of plus 7, and then that becomes plus 2 in the products. So is manganese gaining or losing electrons? Gaining. So is it oxidized or reduced? Reduced. Great. So another way to think of this is manganese is becoming less positive, right? We went from plus 7 to plus 2. So it's less positive after the reaction, so it must have gained some negative charges, so it gained electrons. All right, so now we can write out the oxidation and reduction half reactions. Okay. So our oxidation half reaction, iron 2 plus becomes iron 3 plus. And then for reduction, manganese in permanganate becomes manganese 2 plus. Okay, so then what was the next step we needed to do? Let's go back to our series of steps. Okay, so once we've written the oxidation and reduction half reactions, the next step is to balance the mass. So we want to first balance elements other than hydrogen and oxygen, and then we want to balance oxygen by adding water where oxygen is needed. And then we have to balance hydrogen by adding H plus where hydrogen is needed. Okay, so, oops. Oh, did it not save? Oh, there it is. I think I got my slides mixed up. Let me fix that really quickly. Oh, yep, I have a blank slide in the middle there. Okay. So you'll notice that in our oxidation half reaction, we have one iron atom on each side, so that's fine. That's already balanced in terms of mass. But for the reduction half reaction, there's oxygen on the left, and we don't have any oxygen on the right. So that's where we need to balance this using water. All right, so let's balance this reaction. Okay, so let's rewrite what we have. And in order to balance the 4 oxygens on the left, we're going to add water molecules to the right because water has oxygen in it. Now, there's no harm in adding water molecules because they're neutral and manganese is already aqueous, so we know that there's water present in solution. Now, how many water molecules should we add in order to balance the oxygens? So we have 4 oxygens on the left, so that means we should have 4 water molecules on the right. So that will give us 4 oxygens. Now, notice that when we added water, we also added hydrogen atoms on the right. So now we have to go over to the left and add some hydrogen ions to balance the water molecules. But that's okay because we're in an acidic solution. And in acidic solutions, we naturally have hydrogen ions. So how many hydrogen ions should we add on the left-hand side to balance the hydrogens on the right-hand side? So 8. We need 8 hydrogen ions on the left-hand side to balance the 8 hydrogen atoms on the right-hand side. Okay. So now we need to, in the next step, figure out how many electrons are lost or gained in both of our half reactions. So let's start with the reduction reaction that we just balanced. So let's add up the charges on both sides. So I'll do that in red. So on the left-hand side, we have 8 positive charges. So I'll just write plus 8. And then we have 1 negative charge from permanganate. What about on the right-hand side? What's the total charge there? So it's just plus 2, right? Water is neutral, so all right. Now remember, this is a reduction half reaction, so it's gaining electrons, which means we're going to write the electrons as a reactant. So we have plus 8 plus negative 1 plus some amount of electrons, which is going to go to plus 2 as a total. So actually, I'm going to rewrite this as an equals sign. Okay, so now if we rearrange and add and subtract and do whatever we need, the number of electrons will equal plus 2 minus 7. So that is negative 5. So that means we need 5 electrons on the left-hand side. So we're going to add 5 electrons. And that's going to balance the charge on both sides of the arrow. Okay, so let's see. Let's rewrite that reaction. Okay, so that's our redox reaction, or reduction half reaction. So we have 5 electrons plus 8 hydrogen ions plus permanganate, which becomes Mn2 plus 4H2O. All right, so our oxidation half reaction, remember that means that electrons are lost, so we're going to write that in the products. How many electrons does iron lose if it's going from 2 plus to 3 plus? Just 1, right? So we have 1 electron in the products. All right, so now remember our next step, we want to cancel electrons, or rather make sure that the number of electrons in both half reactions is the same. So do we need to multiply the first half reaction by anything? No. The second half reaction only has 1 electron, so we can multiply that by whatever we need. So what should we multiply this oxidation half reaction by? 5. So this would be times 5. Okay, so now I'm just going to rewrite this just to save room. So now this is going to become 5 iron 2 plus, 5 iron 3 plus, and 5 electrons. So now we can add both of these half reactions together. And then let's cancel the 5 electrons on the left and right hand sides of the arrow. So what's left over, we have 5 Fe2 plus, which will be aqueous, and then 8 hydrogen ions, which are aqueous. And then we also have our permanganate ion, which is aqueous. And then in the products, we have 5 iron 3 plus ions, which are aqueous, a manganese ion, which is aqueous, and 4 water molecules, which are a liquid. So this is a longer process, right? Because we had those oxygens in permanganate, and we needed to balance that with the water molecules that were already present in solution. And then once we did that, we had to balance the hydrogens with hydrogen ions. Now, we were able to use hydrogen ions because this was an acidic solution. If this was a basic solution, however, we would have one more step. We'd have to balance the hydrogen ions with hydroxide ions. So let's go through a problem where we have to consider a basic solution instead of an acidic solution. So in example 3, we want to balance this equation occurring in basic solution. So we have an iodide ion reacting with permanganate, and we're ending up with iodine plus manganese, 4 dioxide or oxide. Ooh, naming. That's something you should review. It's something I should review too, apparently. All right, so to balance these redox reactions occurring in basic solution, we're going to follow the half reaction method outlined in examples 19.1 and 19.2, which we just did, but we're going to add an extra step to neutralize the acid with hydroxide. All right, so let's go through that together. So again, the first thing we always want to do is assign oxidation numbers to each of the molecules or ions. So iodide has a -1 charge, so its oxidation number is -1. And then we saw earlier that in permanganate, oxygen is -2 and manganese is +7. So we've already went through that process. Now in the products, iodine is neutral, so that is going to have a value of 0. And then manganese 4 oxide, we have 2 oxygens, each with a -2 oxidation number. So that would be a total of -4. So what would the oxidation number be for manganese? +4. Okay, so now let's see if we can tell whether something's been oxidized or reduced. So let's write out our half reactions and we'll determine from there. All right, so in the first half reaction, iodide is going to turn into iodine. And the value for iodide was -1. The value for I2 is 0. So is iodide losing electrons or gaining electrons? It's losing electrons, right? It's becoming more positive. So that would be our, let's see, is that the oxidation or reduction half reaction? So if it's losing electrons, that's the oxidation half reaction. Great. And then I'm just going to erase those numbers there. All right, now what about the other part of our reaction? We have permanganate, and that's becoming manganese oxide. And we said that the value of oxygen was -2 for both of these molecules, but the oxidation state of manganese has changed. It went from +7 to +4. So is manganese losing or gaining electrons? It's becoming less positive, right? So it's going to gain electrons. So is that oxidation or reduction? Reduction. Now, one other way to think of this too, just as a kind of a shortcut, once you figure out what's being oxidized, the other thing is being reduced. However, sometimes we do have other elements in there that can complicate matters, kind of like oxygen in this example. So we do always want to step through and make sure that we have the right element that's being oxidized and then the right element that's being reduced. Okay, so I'm going to erase these oxidation numbers here. So now in the next step, we want to make sure we have balanced atoms on both sides, right? So in our oxidation half reaction, we have 1 iodine atom on the left, but 2 on the right. So what do we need to do there to balance it? So we need to add a 2 in front of the iodide ion in order to balance those atoms. Now, what about for the reduction half reaction? So we have 1 manganese on each side, so that's balanced. But we have 4 oxygens on the left and 2 on the right. So again, what do we do if we need to balance oxygens? We have to add water molecules. So how many water molecules do we need to add on the right-hand side? 2, right? We want to make sure we have 4 oxygens on each side. So we're going to add 2 water molecules to bring the total number of oxygens on the right to 4. All right. Now, the next step, we have to balance those hydrogens that we just added. So I'm actually going to make some, I'm going to rewrite this, make some room down here. Okay, so how many hydrogen ions do we need on the left-hand side to balance the hydrogens we added on the right? 4, right? We have 4 hydrogen atoms on the right, so we need 4 hydrogen ions on the left. Okay, so if this were an acidic solution, we would just stop there. And then we would go on to the step where we figure out how many electrons we have. But we're in basic solution, so we need to balance the hydrogen ions with hydroxide ions. Oh, didn't mean to do that. Meant to change my ink color. Okay, so let's rewrite this reaction again, just to kind of highlight what changes we're making in each step. All right, so now we're going to add hydroxide ions to balance the hydrogen ions. So how many hydroxide ions do we need to balance those hydrogen ions? 4. So the negatives will balance the positives. Now, what's great about that is, remember, hydroxide ions and hydrogen ions make water molecules. So we can just turn this back into water. However, because we added 4 hydroxides on the left, we also have to do the same thing on the right so that the oxygens and hydrogens will all be balanced on both sides because we want atoms to balance. Okay, so now what we have is 4 H2O coming from the hydroxides and hydrogens on the left, plus permanganate, and then that becomes manganese 4 oxide. That's a 2, not a 4. It's hard to talk and write at the same time. All right, and then we have 2 water molecules and 4 hydroxide ions. Whew, okay, so that's our full reduction half reaction. So remember, if you're balancing in a basic solution, you have that extra step where you have to balance your hydrogen ions with hydroxide ions, but you have to add the same number of hydroxide ions to both sides of the arrow. Okay, so let's rewrite our 2 half reactions now that we've balanced them. So for oxidation, again, we have 2I minus, and that's going to become I2. And let's figure out how many electrons are lost during this oxidation half reaction. So how many electrons does, or how many electrons are lost overall? 2, right? The other way you can think of that is we have to balance the charges on both sides. So we have 2 negative charges on the left, and we need 2 negative charges on the right. Now, what about our reduction half reaction? So remember, in this half reaction, we have 4 water molecules on the left plus permanganate, and then that's becoming manganese 4 oxide plus 2 water molecules plus 4 hydroxide ions. So let's figure out what the charge is on both sides, and then we'll figure out how many electrons are gained on the left-hand side. So on the left-hand side, we have 4 neutral water molecules and 1 permanganate ion with a negative charge. So the total charge on the left is just -1. And then we're going to gain some amount of electrons. On the right-hand side, we have a neutral manganese 4 oxide molecule, 2 neutral water molecules, and then 4 negatively charged hydroxide ions. So the total charge on the right is -4. So -1 plus the number of electrons is equal to -4. All right, so the number of electrons will be 3. And it is negative because they're negatively charged, so that works out. All right, so let's add, actually I'm going to make some room on the left-hand side for these electrons. So let's add 3 electrons to the left. All right. So we can see that in our first half reaction we have 2 electrons. In our second half reaction we have 3. So now we have to make sure that those numbers of electrons are equal. So what do we need to multiply the first reaction by to make it equal to the second reaction? 3, right? And then we're going to multiply the second reaction by 2. So that way we'll end up with 6 electrons on each side. So let's rewrite that. So we have, for our first half reaction, 6 iodide ions, 3 I2, and 6 electrons. And then for our second half reaction, we have 8 water molecules. Let's see, 2 permanganate ions and 6 electrons. And then in the products, we have 2 manganese 4 oxide molecules. We have 4 H2O and 8 OH minus. Ooh, that's a lot. Got a little cramped over there. All right, so now we can cancel our electrons on each side of the arrow. And we can write out our full balanced reaction. But one more thing we can cancel. Can we cancel anything else? The water molecules, right? So if we look on the right-hand side of our second half reaction, there are 4 water molecules, which will cancel with 4 of the water molecules on the left. So we'll end up with just 4 water molecules on the left. All right, so sometimes there's multiple things we can cancel, but I do recommend waiting until this step to cancel things because you never know what you might need to balance before that. All right, so now what we have left over are 4 water molecules, which will be liquid, 6 iodide ions, which will be aqueous, 2 permanganate ions, which will be aqueous. And then on the right-hand side, we have 3 iodine molecules, which are aqueous, plus 2 manganese 4 oh, I did that again in the upper equation. That should be a 2. All right, so that would be aqueous as well. Or no, that would be a solid, excuse me. And then we finally have 8 hydroxide ions, which are aqueous. Okay, so that was a long process just to balance one equation, right? But again, this is really important because we need to know how many electrons there are in this process. Later on, we're going to see that the number of electrons makes a huge difference in the amount of electricity or current that you can generate in a battery or a fuel cell, for instance. So we have to go through this process of balancing so that we can then later use that information. Okay, so on worksheet problem 1, you're asked to balance each redox reaction below, assuming that it's occurring in acidic aqueous solution. So I'm going to let you all try this on your own, and I'll post the worksheet key so you can check your answers. And again, you're in acidic solution, so you don't have to do that last step with the hydroxide ions. Okay, so this was our little intro to electrochemistry. Next week, we'll continue talking about electrochemistry. So we'll kind of wrap up and get through chapter 19. And then we'll later on start chapter 20, which will be our last chapter of the quarter. So I will see you in next week's video.